We're still on, well, we're doing organics, but in one, we have two teachers. In one area, we're doing kinetics, the other area, we're doing organics.
Okay, that's fine. Good stuff. All right. Well, thanks for that update. Right, I just thought we'd pick up pieces from where we left and looking at this Hess's law. So you were okay with this first example that we looked at? Because I also
Yeah,
sent you these notes. Okay, good. Now, just to check, do you take time just to reflect and review some of the work that we do in the lessons, in these lessons?
yeah,
Good, because it's very important, especially with A level, not just checking, but also trying to have a go at a few more questions outside of these sessions. Because with A levels, the more you practice, you can tell the A star student from the B student or the C student, because the A star student does thousands and thousands and thousands of questions, not even
yeah,
like GCSE. So this really is the ball game to become really good at anything at A level. You've just got to put in so much practice. Okay. So that's the key to really getting a top grade anyway. It's unlike a GCSE where you don't have to practice thousands of questions. If you're very good and you understand the subject material, you just have to do maybe a few hundred. But with A level, it's really about pushing that margin to the thousands. Okay. So that's the secret there. Okay, anyway, let's go and look at this example anyway. So we're looking at still using enthalpies of formation to calculate an enthalpy of a reaction. So we've been given this reaction here. Now I sent you this sheet as well, so you must have this sheet in your email. Do you have that still accessible?
yeah, in my email, I do.
Yeah, it's just there might be a chance for you to trial out some questions. So if you've opened it on your own page, it might be easy to be able to flick between the pages. Okay.
Okay.
Okay, good. All right, so let's look at this example now. Again, we've been given some enthalpies of formation, yeah, and the equation has been given. Sometimes the equation is not given, but rarely, oftentimes the equation is given. All right. So here we go. That's the equation given, and also it's important to check that the equation itself is balanced. You okay with that part so far?
Yeah,
Good stuff. Then we draw an energy cycle, and we try and show the paths that we can use to try and get to the products as well as the reactants. So if I just rewrite this equation, if I just pick my black pen here. So now I've got this reaction on one side, 3CO, yeah. I'm not going to bother with writing the states here because I'm literally just writing out the equation. So it's not like we're writing anything to do with enthalpy of formation or anything like that. So we can save ourselves some time there. So 2Fe plus 3CO2. Now there are a few things here that we can see because we're using enthalpies of formation. So we've got carbon monoxide, yeah, on this side. And also, of course, we've got this iron oxide. So what can we form this carbon monoxide from? What elements do you think we need to form the carbon monoxide from?
carbon, oxygen.
Correct, carbon and oxygen. So carbon plus oxygen. Yeah. What about, now we've dealt with that. What about the iron oxide? What elements, what do I need to form the iron oxide?
Iron and oxygen.
Iron and oxygen, but I've already got an oxygen here, and really I should write this here as O2 because this is formation. So we have to show the element, the molecule of oxygen as O2, not just as O. Okay, so there we go, plus Fe, but it has to be balanced with what's up at the top. So I need to write a 2Fe here. Well, how many oxygens do I have? I've got at the top. How many oxygens do I have on the left-hand side here?
You have 6.
Yeah, so I need a 3 here, don't I? And carbons, I've got 3 carbons, so I need a 3. So this is the path that will, I'm going to put that in a different color. This will take me to this side of things, and I show my arrow, okay? Now at the same time as well, if I look very carefully, this is exactly what I need here to form carbon dioxide as well. Can you see that? And what I've
Yeah.
got. So this arrow forms what's on the right hand side as well. All right. Now then we start and we can label these. You know what? I'll call this, I'll put a different color here. We'll use a green color here. So we're going to call this delta H2, and we're going to call this delta H1. And this here is the delta H of the reaction. Okay. So now looking at these paths, we want to get here. So we can see firstly, in the sense of the arrows, this arrow and this arrow are moving in the same sense. Do you agree?
Yeah.
Correct, because it's almost as if they're following a clockwise motion almost. So therefore, delta H1 I can write plus delta HR is equal to delta H2. Are you happy with that?
Yeah.
Good. So now I can rearrange. What I really want is the enthalpy of this reaction. So I've got to rearrange my equation and take that over to the other side, which means then that the enthalpy change for this reaction will be given by delta H2 minus delta H1. So far, so good.
Yeah.
Yeah. So now I'm applying Hess's law at this point. This is now applying Hess's law. All right. And we'll just state it here. This is Hess's law application. So if I write out what I have, then I now have that delta HR for this reaction is going to be given by delta H2. Well, if I look at delta H2, and this is very important, we need to ask ourselves, well, what's forming here? The enthalpy, what's the enthalpy of formation of iron first? Any ideas?
Is it 0?
Correct, okay? Because it is an element. So we can say that here, iron or Fe doesn't have a formation value. Okay, as it is an element. So one moment, I'm just going to turn the light on. It's a bit dark in here. Better. Okay, as it is an element, right. So then what we have then, what we see on, what we see here, therefore, what is going to be in this, I'm using this equation, by the way, now. So delta H2 is really composed of 3 enthalpies of formation of CO2. Do you agree? That's all that this delta H2 is made of. Now this here minus, now let's look very carefully at delta H1. Delta H1, well, I've got carbon monoxide. Okay, that's not an element, so definitely that has an associated enthalpy of formation. Likewise, the iron oxide has an enthalpy of formation. What do I have there? I've got 3 times, because it's 3 moles that I'm forming here. Okay, delta H, formation of CO. This here added to, well, if I look at this, how many moles of iron do I have? I've only got 1, so I don't need to worry. It's simply 1 mole delta H of formation of Fe2O3. And the table here gives me some values, doesn't it? So I've got what I need. So now the question or the game really is just about plugging and playing in here. So there we go, delta HR equals to 3 multiplied by 394. Okay, that's 4, by the way, minus brackets 3 times 111 plus, that's a minus 822, and all this is in kilojoules per mole. So if I compute all these numbers together, I get minus 1182 plus 1155. Yeah, and this gives me minus 27 kilojoules per mole. Okay,
Yeah.
and that's how we do it. Are there any questions there?
I don't think so.
No? Everything's clear. Good. All right. So that was us applying Hess's law in this case in the formation, or rather in the redox reaction there. I've already filled that one. So key thing to know is that there are a number of ways that we can work out the enthalpy of a reaction, okay? So one of the ways is where we use the enthalpy of formation of the products and we subtract away the enthalpy of formation of the reactants. That's one method one. Then we have method two, where we can use the enthalpy of combustion of the reactants minus the enthalpy of combustion of the products. Now note very carefully here, because this is where students make mistakes, okay? Here it's products, if you're using the enthalpy of formation, it's products minus reactants. If you're using enthalpy of combustion, then it's important to remember that it is enthalpy of combustion of reactants minus products. So take some time to commit this to memory, okay? Good. So we're going to have a go at trying to attempt to use both so that we are familiar as to what to do if we had to apply any of those to a scenario, so to speak. So here you go, it says find the enthalpy of change of reaction between ammonia and hydrogen chloride gas forming ammonium chloride using the enthalpy of formation values provided. So we've been given a table here and we've got some enthalpies or values given here. So we are going from, of course, there to there. And you can see here again that delta H1 plus delta HR are in the same, if you like, sense. Yeah. So therefore, again, similarly to my start, I would write delta H1 plus delta HR equals to delta H2. So far, so good?
Yeah.
Good. So the next thing now is I literally need to start looking, because what I've been given here is our values of enthalpy of formation. Yeah. So therefore I can say, or I can move this to the right-hand side, which would give me delta HR equals to delta H2 minus delta H1. Right. So next step then, I would say delta HR is equal to, well, enthalpy of formation, delta, if I look at delta H2, it's dealing with the enthalpy of formation of what? Of ammonium chloride. So delta HF of NH4Cl minus delta HF of, now this time we're looking at this root here. So the things that we're forming are NH3, yeah, plus, what do we have here? Delta H of formation of HCl. All right. So note carefully, what do we have this side? We have the products, or the product in this case, okay?
Yeah.
Product minus reactant. But we did this almost formally by rearranging this, and rearranging this helped us to almost work out what we needed to do. Okay, so in we go then. In this case, we can see that we've got one more of each of these things, so we're fine. It's one more of each, because that's what we mean by enthalpy of formation. Right, so plug and play then. We put in minus 314, okay, minus, okay, we're going to put this in brackets, okay, square brackets, because we've got two things here adding. I've got minus 46, which I picked from there, minus 46 plus minus 92. Okay, and if I add everything here, I get a value which gives me minus 176 kilojoules per mole. Are you happy with that?
Yeah.
Good. So this was using method 1. So method 1. Now we can use method 2 as well if you wanted to. Now for method 2 here, what are we going to be using? We're going to be using values for combustion as opposed to formation, okay? So method 2, now I'm just trying to see if we've got, do we have some values of combustion here? No, we're missing some values of combustion. Not sure. Let's have a look on the next page. We've only got formation there. Do we have any values of combustion on this side? Okay, no, all right. Well, method 2, well, okay, I think my notes page here has been, because method 1 is essentially the same as method 2. Don't worry, we're gonna have another example to use method 2 anyway, okay?
Okay.
So don't worry about this one. So for this one here anyway, it says calculate. Now here we go. We've now got values of combustion in this one here. That one didn't have values of combustion. That's fine. Okay. So it says calculate delta H for the formation of, yeah, methanol, and try both methods. So if we go about the first method, okay, and we write out our, oops, use a different color pen, and we write out our energy cycle. Well, what would this be? First, if we write this out, it would be C plus 2H2. Let's just write it out, plus H2 plus O2. Yeah. And this is going to give us CH3OH. Now we need to balance it. So what does it look like when I balance it then? What numbers should I use?
Should you put, do you need to make the H2 to H3, so uh, do you put 1.5 next to the H2?
Okay, try again.
Oh, do you put a 2 next to it?
I put a 2, correct. Okay, next one.
And then do you put half next to?
Yeah, absolutely spot on. You're good. Okay, and then I put a half O2. Now, because this is method 2, I'm looking at enthalpies of combustion. So if I combust this stuff here, meaning I react it with oxygen, yeah, what do I get as my products?
Carbon dioxide and water.
Well done. And I get water as well. Okay. Now I've got 2H2 here. So how much water do I get here? If I've got 2H2 and it reacts with oxygen, I should get 2H2O as well, isn't it?
Yeah.
Okay. Therefore, I'm reacting it with 1.5.
Okay.
Or 3/2 O2. Make sure that you can see what I've done here, yeah? Because 3/2 O2 plus a half gives you 4. And we've got 2 oxygens plus 2 oxygens, which gives us the 4. We've got 4 hydrogens. We've got 1 carbon. Are you okay with that?
Yeah.
Likewise, if I react this with oxygen, I get carbon dioxide and water. How many moles of oxygen do I need to react it with? Have a go at that one. How many moles of oxygen should I react my methanol with so that I get CO2 plus 2H2O?
Is it the same?
Yeah, 3/2 O2. Well done. Okay. And then we're all balanced out there. So that's the 3 there plus 1, 4, and 2 plus 2, which gives us 4. Good. Okay. So now here, I'll then say delta HF. Yeah. So what are we going to be looking at here now? Now here we've got reactants. Because remember, we're using combustion now, aren't we?
Yeah.
So our expression needs to be reactants minus, so the delta HF of the reactants, sorry, not delta HF, the enthalpy of combustion of the reactants minus the enthalpy of combustion of the product. Remember that expression?
Yeah.
Very good, because now we're dealing with delta HC here. So there we go. So I can write right away delta HC of graphite plus 2, because I'm using my expression here, 2 enthalpies of combustion of H2, okay, in square brackets, minus the enthalpy of combustion of methanol. So far, so good?
Yeah.
Good. And now I can see these values here, literally just pick them out. And what does this give me? Minus 393, okay? Plus there's 2, I've got 2 moles of hydrogen here, and I can see that for 1 mole, it's minus 285, but I've got 2, so I've got to say plus 2 times minus 285, okay, back in square brackets. And this minus, I can pick up my value for enthalpy of methanol, which is minus 726. Now be very careful with the signs here because we need the signs, super critical. So this then comes out to minus 963 minus 726. And so I get an overall value of minus 237 kilojoules per mole. So I've used the other method. So this is now delta HC of products minus delta HC. Don't know why I keep even I'm confusing it. Sorry, reactants. Now let's take this off, otherwise it will confuse things. Let me try and erase this. Oh, taking off quite a bit there. Okay. Two H2O, okay, and then it's a delta HC. These are the reactants minus delta HC, and this is the product.
Yeah.
Okay, righty. So that is for using our method 1, of course. And now we can use, if you want to, we can also use method 2, where we use the enthalpies of formation. And I'll leave that as a little bit of an exercise for you to try. All right, is that okay?
Yeah.
Yeah, as a little bit of a homework exercise. Good. Okay, so some for you to try here. Now the values are given that you can use to go through these calculations. They are given in the worksheet. So if you want to go to this one I've sent you on your email, all right, so you've got these values here, but also you've also got these values over here. Okay, and not sure what page number it is, but I'm sure you find them if you have a good look. So do you want to open your document on your email and have a go at these problems, please?
For the first one,
Yes.
um, do I use the enthalpy of formation values?
Yes, absolutely. I would strongly recommend that you use the enthalpy of formation values, because on your sheet you will have enthalpy of formation. Actually, you've also got values for enthalpy. No, you've got enthalpy of formation values on your
Yeah.
page. Yeah, so use the enthalpy of formation for that one. Okay, you've got enthalpy of formation more than you do. Yeah, enthalpy of formation. You don't have enthalpy of combustion because that's silicon, isn't it, as opposed to sulfur. You've not been given enthalpy of combustion for silicon. So do use enthalpy of formation for the first one. Okay,
Okay.
good.
I'm not sure if this is right, but for the first one, I got 425.
400? Okay, should we?
425.
Okay, that's a bit on the high side, but let's just try run through it together then, shall we? So we're using enthalpy of formations, right? So we're looking
Yeah,
at how we can get to that side, form this stuff here, and also how we can get to that side, form this stuff that's here. Yeah?
yeah.
So let's just start off with looking at how we can form what's this side. So what do I need? It's enthalpies of formation. So if I write the reaction, remember that exercise we did where we were writing the enthalpies of formation. So let's try and write an equation for the formation of this. What would I need? Silicon tetrachloride.
Silicon, Si,
Very good. What else?
plus Cl plus H plus O, but
Okay.
H2. O.
Very good. Thank you. Very good. Because it's the natural state at room temperature and pressure. So this exists as H2. Oxygen exists as O2. Anything else missing?
Is it Cl2?
Well done. Did you have it as Cl2?
On my page,
Yeah, on your page when you did it, did you write Cl2 when you were writing the formation? You write it like this.
no,
Okay. But do you see why it has to be like this?
yeah,
But of course here, just for the formation of this, I'm not even concerned about this H2 part. Let's just break this down because it gets confusing, okay? Let's just concern ourselves with this first. And all you need is silicon plus you need 2 moles of Cl2. Do you agree?
yeah,
Then let's concern ourselves with the formation of water. What am I going to need? You're going to need H2 plus O2. Do we need to balance anything here?
do you need to put 2 in front of the H2?
Correct. I need to put it 2. You're absolutely spot on there, okay? Because I can see that I've got 2H2O. Then I look this side now. Yeah, and by looking at this side, do I need to change anything I've got on this side, or is everything looking pretty balanced?
It's all balanced.
So balanced, correct. So I know that these things here can go on to form, so the silicon can react with the oxygen to form silicon dioxide, and the hydrogen and the chlorine can react to form hydrogen chloride gas. Yeah? So I'm going to
Yeah,
call this path here delta H2, and I'm going to call this delta H1. So you can either then say here that the delta H of this reaction, which is what we're looking for, is going to be given by delta H2 minus delta H1. Because remember, this delta H1 was initially on this side of the equation because it's delta H1 plus delta HR, which gives us delta H2. So we take it over to the other side, it becomes minus. So far, so good.
yeah,
Or you can, of course, say, if you remember that trick, sum of the delta H, because it's formation. So we say products minus sum of delta HF of the reactants. You can go directly to that, okay? Now we sub what we need here, sorry, that's delta HR. So now what do we get then? So we're gonna find the, we're gonna try and work out what these delta H's are, so to speak, if you like, okay? So what do I have as my delta? So in this case, rather, I'm just gonna rewrite this here in a different colored pen. So if I go there now, I can see that my delta HR is going to be composed of, let's just look at the products first. So the delta HF of formation of, sorry, products I meant, of silicon dioxide, okay, plus, well, there's a 4 there. There's only a 1 there, so I didn't worry, but there's 4 hydrogen chloride gas produced, plus 4 multiplied by the delta H of formation of HCl. This subtract, now we hear the reactants, the delta H of formation of silicon tetrachloride. Plus, now there's 2 moles here. So it's 2 times the delta H of formation of water. Okay. Now, if you look in your data sheet on your page, so those values are given. So what do we have here? We've got for this one here, if I just put those values in here, do you agree that for this here, it would be minus 910, and for this here, it's minus 92, yeah? And this
Yeah.
here, minus 687, and this here is minus 285. You agree?
Yeah.
Good. So if I put all these numbers in there, remembering to multiply that by 4, remembering to multiply that by 2, I therefore get that delta HR of this reaction is given by minus 1278 minus 1257. Okay, the minus and the minus are going to make a plus, but this is still bigger than that side. So overall, it's an exothermic reaction. So I get delta HR as minus 21.0 kilojoules per mole. Did you follow that?
Yeah.
Great stuff. Do you want to have a go at number 2 as well, using enthalpies of formation, just so you get the hang of it first? So I'll leave that there in case you want to have another look as well to see what was going on for this one.
I got minus 27 kilojoules per mole.
Well done, Zinera. That is, you're absolutely spot on. Well done. Excellent. That's the one. Okay. Well done. Way to go. Good. Okay, try the next one now, please.
Shall I use the formation?
Formation as well. Yeah, let's get the hang of formation, and then we'll have a look at the fuel with combustion as well. Okay.
I think I'm going wrong somewhere in the calculations because I got minus 1013.2.
Minus 1013.
Yeah.
That is absolutely spot on.
Oh, it's because
No, you're absolutely right. So what did you think you went wrong with it?
the first few times I typed it into the calculator, I wrote the wrong numbers and I had to do it over and over again. So I think I just thought that I might have made a mistake with copying down the numbers into the calculator.
Okay, but the key thing here is that the enthalpy of formation of nitrogen, did you take this as 0? Very good. Okay, that's the main part to this. So you've absolutely done the right thing. So minus 1013 kilojoules per mole. Okay, well done. Excellent. Now for the next one, I want you to use enthalpy of combustion.
Okay. I got a bit stuck because I don't think I have the CH3OH.
You do. If you look in your sheet, just to, if you can see my screen, it is just before. There it is. Can you see on my page?
Can you keep it on the screen because I couldn't find it on the sheet?
Okay, no problem. I'll leave it there. No problem.
I got minus 1,579 kilojoules per mole.
Oh, that's a bit too high. That is a bit too high. So for this one though, the key thing is that because we're using enthalpies of combustion, delta H is the sum of the enthalpy of combustion for the reactants minus the sum of the enthalpy for the products of combustion rather. So you had that to start with?
Yeah.
Good. So if I combust carbon monoxide, what does it produce?
Water and
What is
CO2.
carbon monoxide?
Carbon,
So if I react this with oxygen, what do I get?
carbon dioxide and water.
No water. The water only comes if I react hydrogen with oxygen.
Oh yeah.
That is what gives me the water. And how much water do I need? What number do I need to balance that with? Good. Likewise, if I burn this here, methanol, which is liquid, what do I get? Carbon dioxide plus water. So in each of these cases, if I want to balance this, this would be 3/2, and this would also be 3/2 O2. So did you have this reaction here?
Yeah.
You did, okay.
Yeah.
And the CO2 on the water?
Yeah.
So therefore we say delta HF is equal to delta HC for the CO, remember it's reactants, plus these 2 lots of hydrogen. This here minus delta HC, there's only 1 lot of CH3OH. Is this what you had?
Yeah.
Okay, so then the numbers, we put in the numbers. For this one, this is minus 283 plus 2 times minus 285, square brackets rather, minus, well, this here is minus 726. Now, if we add everything here, we get minus 127 kilojoules per mole. Can you see where you went wrong?
Yeah, I think I typed the numbers in wrong.
Okay, so with that in mind, then make sure that you double check when you type the numbers in your calculator, because it seems like your calculator is letting you down a little bit. So just double check, okay, that you have punched in the numbers correctly, especially when you're having to do with so many brackets and things like that. Sometimes what I do is I work out each part separately and then I write the number. Work out each part separately, write out the number. Then at the end, just do the addition. Sometimes it can be much easier and much safer to do it that way. Okay.
Yeah.
Okie dokie. So that is it. We come to the end of Hess's Law, and I'll send you some questions to have a look at, some exam type questions. And then in the next lesson, we're going to be looking at the enthalpy change. So bond enthalpies is what we're going to be looking at next. Okay.
Yeah.
Okay, good. How are you feeling about Hess's Law anyway at the moment so far?
More confident now.
Good, well done. Okay, no problem. So Zinera, when would you like the next lesson ideally? Next week?
If possible, yeah, because my mocks are mid-June.
No problem. Okay, no problem. So we'll try and schedule. I'll try and see if I can work for a Tuesday, same time Tuesday. Okay.
Okay.
Okay, no problem. Have a lovely evening, and I'll send you all this board work, and I'll send you some additional work as well, plus the video as well. Okay.
Thank you.
Okay, no problem. See you soon. Bye.
Bye.
Bye.